Hello everyone, today we'll talk about the solution to the problem maximum number of points with cost. Feel free to pause the video and read the statement, and we'll go on to talk about the solution. So, a problem like this, probably for most experienced people, immediately feels like dynamic programming. Because we have this very standard situation where we have this matrix, we have to go row by row, and we choose something in the row, then we choose something in the next row, and we pay penalty, in this case equal to the horizontal displacement between the two elements we've chosen, so the distance between them. And we have to maximize the sum of points minus the sum of penalties. And so it's natural to do a dynamic programming here because we can calculate, for instance, row by row, and then at every row we know the best score we would be able to get while taking, so for instance here, while taking this element. And extending it downwards can, for instance, in a naive fashion be to go through all the positions above, so through, because we have to select something above, and then when we take that thing that's above us, we have to pay the penalty equal to the horizontal displacement, and this is one option for what we can get taking this element. We go through all the options and then we get the result for this element. And now we also would like to think about how to make it faster, because this naive option for every element in the current row goes through all the elements of the previous row, but it's obvious that not all the elements in the previous row are interesting. So we can either focus on the idea that they are not all interesting, there is some monotonicity here. So for instance, if we know that we have a row and we'll be calculating values somewhere far to the right in the next row, and we have something like A and B here, then we know that A will have the penalty smaller by the distance between A and B. So if A is either large enough so that A plus that distance is smaller than B, in which case it's always preferable to take A instead of B, or A is too small, B is large enough that even if we subtract this distance, it's still better than A. And in that case, we always want to take B. In other words, if we know that our target positions will be to the right, we actually have to only remember a single number. And that number will be the best thing that happens to the left. And of course, the same thing would happen from the right side. So that would be one approach of doing that. Another approach, maybe simpler, is to reformulate our task. And that task will be that we want to, of course, since we want to get the maximum number of points minus the sum of penalties, then we have two operations. One operation is to go down from the position that we're currently in. We can imagine that we can start at any position above our matrix. And when we go down, we earn the number of points equal to the value of the field that we've gone down to. So for instance, we enter the matrix here, so we get the value that's written here. And now we have, again, an option to go downwards, or we also have an option to go left and right. And when we go left and right, we have to pay a single value, right? We have to pay 1. So this is the same thing as our task, because to model this situation, we'll enter here, get the value at this position. Now we have to pay 1 to go to the left, pay 1 to go to the left, pay 1 to go to the left, and then go downwards. Well, maybe here, of course, those going to the lefts will have to be calculated the number of times equal to, because I've here written as if the distance between those two will be equal to 1. The distance between them, of course, is not equal to 1. The difference between the indexes. So this will be indeed equal to the number of going to the lefts. It doesn't really matter, it's just plus or minus 1. But so in this case we have to enter here, then go to the left 3 times. For each one we pay a single coin. Then we go down, take this element, and again we either go down or some to the left or some to the right. And this is equivalent to this one. And it's also easy to see while looking at one solution while the other is equivalent. And now for the code, we get the height and width of our matrix in a standard fashion. We go through every row and we calculate the best value that we can get while taking what we have at that position, but not just taking the element at that position. So for instance, if we take the value here, it's not going to be just the best thing that we can get while taking this element, but the best value that we can get while ending up at this position. So maybe we will take this element, so we go here, then we go a couple steps to the right, end up at this element. So we want to get just the biggest value in our modified problem that we can get at this element. So in essence, we start by going in one direction and trying to go down, in which case we just take the points from the previous row, of course if the previous row existed, otherwise it's 0. And we take the points for the current position. And now we also have to model going in one direction and in the other direction. So for going in one direction, we will just take the column with the number 1 smaller, of course if it exists. And then we also have to go the other direction, so now we go in decreasing number of column and take the column that has number +1. In both cases we have to subtract 1 because we have to pay a single coin to get that step. And so after all of those, for the row that we're looking at, we get the biggest score that we can get, ending at that position in that row. So at first, for instance, if we go for the first row, this is either the original value that was there, or some other value from the original row, minus a couple of steps that we had to take to get to the given position. And at the end, of course, the maximum over all of the last row is our final answer. Implementing the solution for this one would be very similar, and you could either maintain going from the left and from the right the best option, or try to maintain it within the array, in which case the solution will be essentially equivalent to what I've written here. However, this different perspective of allowing for moving left and right and paying 1 for every move, I think is quite useful in this case.